Hi, students. Today we're going to talk about the idea of heat. And this is actually from chapter 6, should be somewhat review to some extent. And then we're going to head on to the chapter on thermodynamics. And that chapter is a combination of discussions of heat and also a new term called entropy and also another new term called free energy. So, after a lot of thinking about this, I decided that I really want this lecture to be as close to what I would normally do face to face. And so, two things that I talk about to students is the importance of this section on other classes that you're going to have. So, whether you're an engineering major, biochemistry major, biology, physics, doesn't matter. The idea of studying heat and energy in science will cross all of those disciplines. Good news is that this is at an introductory level. This is not at a very extensively hard and heavy upper division level. What it's going to be, and this is the good news, is that at a higher level, there's so much math that is behind this. A lot of very difficult math, differential equations, and physics and all this stuff. So we don't have to approach it from there. So that's good. So this is still introductory. Okay, so what I want to do now is to talk and ask you the question of what happens in a car. And when we're meeting at the Zoom discussions, we can talk about this a little bit more face to face. But so let me ask you that question of what happens in the car. What are the chemical changes that go on? Why are they there? Why is it designed the way it is? So I know you can stop right now and think about that and resume when you have something in mind. So go ahead and stop and think about this. And then when you're ready, get back to me and I'll be talking again. So what happens in a car is that our main reaction is the combustion of octane. And that produces, in a perfect world, carbon dioxide gas and water. You know, there's a lot of pollutants, but we won't be addressing that issue. So we're just looking at it as a perfect world. And my question to you would be, is this endo or exothermic? Is it need heat or releasing? And the answer to that would be definitely exo, negative enthalpy. So going back and thinking about previous processes that we've talked about, there are activation energies at play here. So from our energy diagram that we've seen, here's reactants, here's products, there's still an activation energy. Think about right now that your car is not on fire, right? It has gasoline in it. To get that process to get started, what kind of process happens in a car is that there's a spark plug, and it's going to help light this and get the combustion going. Remember that this heat is coming from the fact that on this side of the reaction, bonds have to break, energy is required, right? You got, and I won't draw the whole Lewis dot, too many carbons, too many hydrogens. You got your oxygen, double bond. Okay, you're getting the point that we have to have energy to break those bonds. And then on the other side of this, bonds are forming. So energy is released. And there's a whole lot of energy released when this carbon oxygen double bond forms and oxygen hydrogen bond forms. So what's greater in this is the amount of energy released. And so you have a net energy, and that's why it is exothermic, giving off heat. Okay, so I really love this part because it ties in a lot of things you've been learning over the full year of chemistry. So now, what are we going to do with this? So we're going to ask the question, where does this heat go? So take a minute to answer that question. You can pause me to think about it. Well, what's the whole goal? Why do we use these fossil fuels that we know are bad for our environment? Is that it provides a lot of energy. The energy gets converted into mechanical work. So I know that, like myself, I've never been into, cars and stuff like that, but some of you probably have a really great explanation of what goes on in a car. And so you can describe the process and the whole nitty gritty of that. But for me, I'm going to summarize it. The wheels on the car go round and round, right? That energy goes into moving that car. Okay. And the wheels of the car. Okay. So energy is converted into mechanical work. In a perfect world, every last bit of heat would be converted into work. And that would be lovely, but we don't have perfect world. And we have an imperfect world. And so what will happen is that not all of that heat goes into work. Some is useless heat. So this top part is useful heat. Okay, and so let's think about that. I have an electric car that I normally drive to work. I haven't been driving at all. But in your car, when you stop the engine of that car, and if somebody said, "Hey, open the hood to check the engine," after you're done driving and you open it, you're going to feel heat. And that heat was useless. It did not go into moving the wheels on your car. So this is a really, really fundamental discussion. Those engineers in the course, this is going to be something that is so critical for you guys because there are no perfect machines that will convert heat energy 100% to work. There's always going to be a loss. Okay. And this will come up for us in the next section. And let me tell you why, because what's going to happen here is we're going to define what this useless heat is. Okay. Now, before we get to that here, and it's going to come up in the next slide. So there's going to be terminology. We're going to have our system, which is the combustion of octane. So the octane burning. And then outside of that is the surroundings. And I'm going to see if I can get fancy with a different color here. Okay, so now picture that the combustion of octane, it converted that burning into useful heat and work. But then there's this other heat that's useless. And what it's going to do is get transferred into the surroundings. Now, I don't know how to spell transferred, if it's 2 or 1 R. Okay, so heat is transferred to the surroundings. Now, it might be useless in turning the wheels of the car, but it is not useless in general. Like, it's still heat, and it's going to go to the surroundings. And so let me ask you this, and you can pause it. What is it going to do to those surrounding air molecules? Well, you should have probably said, right, that the air molecules are going to start to move around more. So it's going to increase the motion of molecules. And what that's going to do is it's going to increase what your book will call microstates, arrangements, ways that those molecules can arrange themselves because they're moving around more. And what is that going to do? Is it's going to increase the randomness of the surrounding air molecules. And that leads us to one of the most famous things in science, which is the idea of entropy. Which is the idea that if we see an increase in the possible arrangements of those molecules, number of microstates goes up, the randomness goes up, that we see an increase in entropy. So entropy is the idea of this useless heat that's transferred from the system to the surroundings in this exothermic process. And I know this is difficult, so what we're going to do, I'll tell you in a second, is we are going to take it in parts. Okay, now, before we move on, I like the example of a car, but these ideas have been around since the design of the steam engines, which goes back a long time, right, in the Industrial Revolution. And the scientists of those times, or the engineers, I should say, of those times, they were always frustrated with the fact that what they expected the steam engine to give them in terms of mechanical work didn't match their calculations, because they grew to understand this idea of entropy and this useless heat. So this idea has been around for a very long time, and it's something that's very, very mathematical, but we're just looking at it conceptually, okay, for now. So one of the things I want you to consider, though, is that every process that you've ever studied in 152, 200, 201, we can talk about the two important concepts here. And one is enthalpy, heat. The other is entropy, and then how they interplay with one another. Okay, and where does this important come into, especially in engineering, is that when you design machines, you have to take into account how much you're going to lose in terms of the conversion of heat to work. Okay, so all right, now that this slide is kind of the big picture of where we're headed. What we're going to do right now is take this in parts, and we're going to start with enthalpy. A lot of what I go through will be review. So that's good. And then in a separate video lecture, we'll try to tackle entropy. And then in another video lecture, we're going to do what I call the big picture and bring the two together. Okay. And think about the big picture of how enthalpy and entropy determine what's called the spontaneity of the reaction. Okay, but we'll come back to spontaneous business later. Okay, so let's review heat. Energy is transferred, okay? And so heat's not temp. Temp is a measure of the average kinetic energy of particles in a solid, liquid, and gas. If you remember from your Chem 200, there was an equation. 3/2 nRT to describe the kinetic energy and temperature. How temperature determines kinetic energy. Average is an indication of that. It's a measure of that. Okay. Energy is what we're going to focus on next. Okay. The other thing as we keep going, I already highlighted this. We need the vocab. System is the part of the universe that we want to focus on. And for us, it's going to be the reaction that we're studying or the process that we're studying. That's going to be our system. And the surrounding is going to be anything else. Okay, so in our car example, the reaction we were thinking of there was the combustion of the octane, and then everything else, the air around it was the surroundings. Put it all together, and we're going to talk about the universe. So the universe will be the system plus the surroundings. Exothermic, that is energy flows out of the system. Endothermic, heat flows into the system. Okay, those you already know. Exothermic, delta H then is negative. Endothermic, delta H is positive. Okay. One of the things that's going to come up is, I like this picture better. So here is a combustion reaction. It's not the octane, it's the methane. So the system is exothermic. And then if you notice, it's a prettier picture of what I did. The system's going to give off heat, and that heat is flowing to the surroundings. Endothermic's the other way. Here's our system. There's our surroundings. Heat flows into the system. Okay, so I wish we had dramatic music. I guess I could have done it, but I'm not fancy enough yet on that. Thermodynamics is the study of energy and how it's converted. And the first law of thermo is one that you already know. It is basically the law of conservation of energy, that energy cannot be created nor destroyed, but just converted into different forms. So that is our first law of thermodynamics. Oops, I didn't want to do this one. Next. Oops. Okay, I didn't want to do these guys because you may have done them in an earlier class. Okay. No, let's do these. Okay, I like this one because These are ones that we are going to need for our discussions along the way. So let's analyze if we can figure out water freezing, if it's endo or exothermic. So take a second to think about that. Okay, so I'll be honest with you, a lot of times it's easier to think of things going from frozen to melted the other way. So if you're going from ice, right, water solid to liquid, we know that it's easier to picture that that had to absorb heat. So the reverse process would be exothermic, heat releasing. Okay, so heat's coming off of there. Okay. Let's label the next one, exo or endothermic. Your hand gets cold when you touch ice. Okay, so your hand gets cold when you touch ice. So the heat is flowing from your hand, right, to the ice cube. So that is exothermic. And that's why it gets cold. Okay, ice increases in temperature when you touch it, and that's because heat's flowing from your hand into the ice cube. So from your hand, it's exothermic, right? Because you're losing heat into the ice cube. Water vapor condenses, so water liquid. So gas going to liquid is a condensation. So this is another one where I think it's a little easier to go water liquid to gas. We intuitively, because we boil things all the time, know that that's endo. So this is the reverse process of exo. Okay, I'm going to skip this one. Okay. Enthalpy is a process or is a state function. And what that means is that what the final and the initial are what matter. It's not the path that was taken to carry out that process. Enthalpy is heat at constant pressure, and where work is only allowed, that is from a volume change. So QP here, that's heat at constant pressure, and that is our enthalpy term. Okay, if delta H is positive, that means that heat is absorbed by the system. And when delta H is negative, it means that heat is released, right, by that process. Okay. Okay. Couple things as kind of a review then. 1 mole of methane is burned at a constant pressure of 890 kilojoules of energy. Calculate delta H for a process in which 5.8 grams sample of methane is burned at constant pressure. So for these, I'm hoping you've done these before. If not, they're easy. We'd write the reaction of methane burning. Oops. We go back. Oops. Oh, that stinks, doesn't it? So we would write the reaction of methane burning. we'd have to balance the equation. So let's see, 2 here, 4 O's. I think we're good with that. Okay. And then the enthalpy was negative 890. I hope I remembered it correctly. And I can go back one more to see that. Yeah. And that was for kilojoules per mole. Okay. Now, for this reaction then, we're given the enthalpy for this process per mole. And so we were asked to figure out the energy if 5.8 grams of methane were burned. So really all we have to do is figure out how many moles that is, and then use the energy value given. So if I take 5.8 divided by 16.04, I should get 155 kilojoules. 2 sig figs would put us here at 160. Okay, so we probably did that kind of calculation before, just a reminder. Oh, I wonder why did I do the math wrong there? Hold up, sorry. I was talking. Oh, I think I just plugged in my calculator wrong. I'm sorry on that. It's like, da-da, then it was wrong. Okay, it was just, I was talking while I was plugging in and I did something wrong. Okay, so that's pretty easy. Okay, so you can practice this one. I'll click on it, but you can stop and practice it. So there's the delta H. Now, one of the things that I want you to notice, and this is important, is this value wasn't given per mole, the negative 1652. So this is for, as written, for 4 moles of iron. So this enthalpy as written is for the reaction as written. Okay, if this were 2 moles of Fe, that would be down by a half. If this was 8 moles of Fe, that would be doubled. So we do have to pay attention to the balanced equations that we have. So take a second to do that one. Good. So since this is for 4 moles of Fe, and this is the value that's given, and it is that value, what they did there, if you were asking where the heck did that 2 go, they just were looking at 3 sig figs. Okay, I won't go through these, each one. I think you can do these pretty simply. They are taking that balanced equation. I'll do the first one. I need to get the number again though, sorry. So that is negative 1652. So 1 mole, what's the heat? That was negative 1652. That was for 4 moles. Oh, that's Fe2O3. Sorry, let me go back. Fe2O3 is 2 moles. So it'd be half of that because this was the one that was being referenced in that balance equation. Okay, so stop and do these, and then when I click, you can see the answers to them. Okay, calorimetry is